Hi everyone, welcome to the Achievers Up. This is Teacher John here speaking, and I'll be going through the Christmas question that we posted in our Facebook and Instagram page just a while ago. So let's take a look at this question. The Koch snowflake can be constructed starting with an equilateral triangle, then recursively altering each line segment using the following instructions over here. So first off, we'll divide the line segment into 3 segments of equal length. And then afterwards, we'll draw an equilateral triangle that has the middle segment from step 1 as its base and points outward. And finally, we'll remove the line segment that is the base of the triangle from step 2. So what we are seeing over here is some set of instructions. We start with equilateral triangle, and then afterwards we'll be performing some instructions on to the line segments of the equilateral triangle. So in this case over here, the first step is to split up the line segment into 3 equal parts. So maybe one color over here, another color over here, and another color over here. So there are 3 equal parts over here. And then afterwards, we'll follow step 2. We'll draw out an equilateral triangle over here as well. So we're going to continuously do this for all the line segments of the equilateral triangle. So that is how we obtain figure 2 from figure 1. And we can extend this particular set of instructions onto figure 2 as well. And for each of the newly created line segments, we apply the same set of instructions, we obtain figure 3. So let's take a look at what the question is asking. Find the area of triangle, taking the area of the triangle in figure 1 as 1 unit. Alright, so the area of this is 1. We need to find the area of figure n. So looks a little bit daunting. We can see that we need to find it naturally in terms of n. And we'll need to be able to identify a little bit of patterns. So let's take a look at the simplest case over here. Now in this case over here, we can take a look at figure 1 and 2. How did they evolve? What's the particular pattern? So in this case over here, you notice that I actually added in the base as well, instead of removing them. So what's the reasoning behind this? Let's take a look. So notice that in figure 2, right, the larger triangle is from figure 1, is similar to the smaller triangle that is created. Why? What's the reasoning behind this? In this case, both are equilateral triangles. So of course, by our AA similarity test, they must be similar in nature. So we definitely have the big triangle being similar to the small triangle that is newly created from the big triangle in this case. So the ones in figure 2, this one over here, is similar to this one. That's highlighted in green. Now, we also notice one very important thing. The ratio of the length of the sides of the smaller triangle to the larger triangle is 1:3. Now, why is that so? Now remember, we divided them into equal segments. So each of them must be of 1 unit. And hence, naturally, the length of the sides, since all the sides of an equilateral triangle are equal, the ratio of the length of the sides of the smaller triangle to the larger triangle is 1:3. So that is something that should be expected from the question. And so based on that, since we are finding area, it will make sense for us to try and find out what's the ratio between their areas. Well, remember, the ratio between their areas of similar figures is really just the ratio of their square of their lengths. So in this case, the ratio of the area of the smaller triangle to the larger triangle is just 1 squared is to 3 squared, which is the same as 1:9. So you can kind of see that if the area of figure 1 is just 1, the area of the smaller triangle must be really just 1 over 9. And this one will just be 1. That's the crucial idea. Now, so after that, we solve with half the battle won. But now we need to understand, how are these triangles created? How do they depend on the previous figures? Now we notice that one very important thing is that the number of new triangles created is dependent on the number of line segments that is in the previous figure. Now, so you notice that, let us take a look carefully over here. In figure 1 and figure 2, figure 1 actually has 3 line segments. And then because of the way that our cell instruction acts on the 3 line segments, 3 new triangles are produced. 3 new smaller triangles are produced. And you notice that one very important thing, each line segment creates 4 more new line segments, if you notice. So in this case, we can start with one single line over here. Afterwards, this will be what happens to it after we apply the cell instructions. Notice that there is just really one line segment over here. And then afterwards, it becomes 1, 2, 3, and 4 line segments. So that's another very important thing to notice. Now in this case over here, I'm going to let Ln represent the number of line segments in figure N, and An represent the area of the newly created triangles in figure N. So now in this case over here, let's take a look carefully. Now in this case, let us take a look at n is equal to 1. And when n is equal to 1, there are only 3 line segments in the equilateral triangle because there's only a single equilateral triangle. And of course, we will let the area be just 1 in this case. Now what about 2? When n is equal to 2, well, you can see that each line segment is going to create 4 new line segments. So the total number of line segments in this case will just be 3 times 4. So keep in mind, I actually written 3 times 4 because you can see that there's going to be some sort of a pattern going on over here. And what's the area of the new triangles? Well, you notice that there are 3 line segments previously, and each of them is going to be 1/9 of what the original size is in this case. So it's just going to be 3 times 1 over 9. It's our area. Now, so we can apply this similar logic to n equal to 3. Now, you notice that in n equal to 3, it's just going to be 3 times 4. And then we will times 4 again because now there are 12 line segments. Each line segment is going to produce 4 new line segments. So it's going to be 3 times 4 squared. And naturally, we're going to look at this as well. The area of the newly created triangles is just going to be 3 times 4 times 1 over 9 squared. Why squared? Because in this case over here, the previous area is just 3 times 1 over 9. And each of them is going to produce another little triangle over there. So in this case, the area is just going to be 3. It's going to be 1 over 9 of 1 over 9. Now, finally, we can actually try and derive a general formula for K. Now, in figure K in this case, you can see how many line segments are there over here. Following this particular pattern, it should be pretty obvious that it's just 3 times 4 to the power of K minus 1. Now, and of course, following this particular pattern in this case, we can immediately see that this is just 3 times 4 to the power of K minus 2. Right? And then what is it multiplied by? It's definitely multiplied by the area. Now in this case, what would be the area? Now, in this case, the area would just be K minus 1, following the pattern as well. That is the idea that I would like to bring to everyone over here. Now, so what's the area of figure N? Well, the area of figure N is just going to be the sum of everything in this box, in this column. Why is that so? Because we defined AN to be the area of the newly created triangles. Of course, it excludes n equal 1 because by default, we start out with figure 1, which has an area of 1. So we're going to sum all these up. Now, so what's the area now in this case, you might be asking? We are going to look at this pattern. So the area of figure n is just going to be 1 plus 3 times 1 over 9 plus 3 times 4 times 1 over 9 squared plus all the way to 3 times 4 to the power k n minus 2 in this case, because we are finding an area of figure n minus 2 times 1 over 9 to the power of n minus 1. That's the main idea. Now in this case over here, we can factorize out a little bit of common things, excluding the 1 over here. Keep the 1. Can factorize out 3 times 1 over 9. Now in this case, I'm going to obtain 1 plus 4 times 1 over 9 plus all the way down towards 4 to the power n minus 2 times 1 over 9 to the power n minus 2. That's the main idea. Now, some of you guys might be very sharp in this case. Of course, this is equal to 1/3. And naturally, you guys probably would see this. This is actually a geometric progression, or a GP. So what's the first term? Well, the first term, naturally, it's really just equal to 1. What's the common ratio in this case? Well, you can see that the common ratio would be 4 over 9. And what about the number of terms? Well, the number of terms is really just n minus 1 of terms is equal to n minus 1. Now, remember our formula for geometric progression. So I'm going to write this down. 1 plus 1/3 multiplied by, start with A. A in this case is 1. 1 minus common ratio to a power of number of terms. So common ratio is 4 over 9. The power of terms will be n minus 1 over 1 subtract common ratio, which is 4 over 9. So simplifying this a little bit, we actually obtain 1 plus 1/3 multiplied by 9 over 5 divided by 1 minus 4 over 9 to the power of n minus 1. We're almost there. It's pretty straightforward now. We can actually simplify this a little bit more. We obtain our final answer of 1 plus 305 multiplied by 1 minus 4 over 9 to the power n minus 1 as our area of figure n. So in this case over here, we notice that there is a lot of things that we actually need to apply. First off, we need to understand that the triangles are similar in nature. We can find the relationship between their areas. And of course, that's something that we are taught in O-levels. A levels, we'll be doing things like the geometric progression and finding the nth sum to n. In this case, it will be Sn. So with that, that's pretty much about it for our Christmas question from the Achievers Arc. I wish everyone a happy new year ahead, and I hope to see all of you again soon. Bye bye everyone.